Have you ever really thought about what makes a tiny silicon chip, well, work? It turns out it's a lot like cooking. So today we're going to open up the atomic level cookbook and see exactly how a simple element gets transformed into the brain of our entire digital world. So what is it? What's the secret sauce? What gives these little squares of silicon the unbelievable power to run everything from your phone to a data center? Well, the answer is actually pretty straightforward. It's all about adding the right ingredients, the right spices, if you will, in just the right way to completely change the nature of silicon itself. Okay, so here's our game plan. We'll start with why pure silicon just isn't going to cut it. Then we'll get into what doping is. After that, we'll see how atoms can even move through a solid, check out 2 different recipes for this process, and finally, see how they're combined in a really clever 2-step dance. All right, first up, silicon's secret ingredient. Or, maybe more accurately, why silicon desperately needs a secret ingredient to be useful to us. You know, here's the thing that might surprise you. A perfectly pure crystal of silicon, it's basically an insulator. It doesn't want to conduct electricity at all. And for electronics, that's useless. We need to be able to tell it when to conduct electricity and when not to. We need control. And that brings us to the main event, the core process itself. Something called semiconductor doping. This is how we add those all-important ingredients. So doping is just the fancy word for intentionally adding impurities, which we call dopants, into the silicon. Now, this isn't about making it dirty or contaminated. Oh no, it's the exact opposite. It's about surgical precision. This is how we turn that boring insulator into a dynamic semiconductor. And what are these ingredients? Well, the most common spices in our recipe book are elements like boron, arsenic, and phosphorus. What's cool is they fit really neatly into this silicon's crystal structure. But to get them to mix in, you have to get things really hot. We're talking baking the silicon wafers in a furnace between 800 and 1200 degrees Celsius. Now, there are 2 main ways to get these dopants into the silicon. First, there's diffusion, where you kind of let the atoms soak in from the surface, like a good marinade. That's perfect for creating deep features. Or you can get way more aggressive and literally fire the atoms in like tiny cannonballs. That's called ion implantation, and it's great for really shallow layers. For this explainer, we're going to focus on diffusion. And this image here really shows you the difference perfectly. Up top, you see diffusion. It's a gradual process, atoms just spreading out. But down below, that's ion implantation, a direct, forceful approach. It really is like the difference between marinating a steak and injecting it with flavor. 2 different tools for 2 very different results. So if we're just soaking the silicon, how in the world do atoms actually move through a solid crystal? I mean, it seems like it should be impossible, right? Well, let's take a look at the physics. It really just boils down to a fundamental rule of nature. Things don't like to be crowded. Just like if you put a drop of food coloring in a glass of water, it spreads out. Atoms do the same thing. They'll naturally move from an area where there's a lot of them to an area where there aren't so many. That's the engine driving this whole thing. And on the atomic scale, this happens in a couple of ways, which you can see right here. On the left, you have what's called vacancy diffusion. Think of it like a game of musical chairs. A dopant atom sees an empty spot in the crystal lattice and just hops into it. Then on the right, you have interstitial diffusion, where a smaller atom can actually squeeze through the gaps between the main silicon atoms. It's like taking an open seat versus just shimmying down the aisle. Okay, so we get it. We know what doping is, and we know how atoms move around. Now for the really cool part, the actual recipes that chipmakers use to control the final flavor profile of the silicon. So, recipe number 1 is called constant surface concentration. The best way to think about this is to imagine you're soaking a sponge in a big bucket of dye. The surface of that sponge is always touching the full-strength dye, right? That's exactly what's happening here. We keep a constant, fresh supply of dopant atoms right at the surface of the silicon. And this is the kind of result you get. Now, don't worry about the mathy-sounding name ERFC. Just look at the shape of these curves. It's exactly what you'd expect. The concentration of our dopant is super high right at the surface, and then it gets weaker and weaker the deeper you go into the silicon. The longer you let it soak, the deeper that profile goes. All right, our second recipe is the constant total dopant method. This one is different. Now imagine you just put a single limited drop of dye onto a sponge, and then you just let it spread out on its own. You're not adding any more dye, you've only got that initial amount to work with. And the result is a totally different shape. This is called a Gaussian distribution. But here's the really interesting part.
Look at that graph on the right. As time goes on and those dopants push deeper, the concentration right at the very surface actually goes down. That single drop of dye is spreading out and getting thinner at the top as it moves inward.
This slide puts them side by side, and you can really see the difference. That solid line is recipe 1, our constant soak. The dashed line is recipe 2, our spreading drop. You end up with 2 completely different final flavor profiles. And having this choice, well, that's what gives engineers all the control they need.
So why have 2 different recipes, you might be asking? Well, because in the real world of chip manufacturing, they don't just pick one. They do something way smarter. They combine them in a clever 2-step dance.
Here's how it works. Step 1 is called predeposition. They use recipe 1, the constant soak, but for a very, very short time. This lets them get an incredibly precise, very thin layer of dopant right at the surface. Then comes step 2, the drive-in. They cut off the supply of new dopants and switch to recipe 2, basically using heat to push that shallow layer deeper into the silicon, to exactly where they want it to end. And that is the absolute key to all of this. This 2-step process gives them the best of both worlds. The predeposition precisely measures out the amount of the ingredient, and the drive-in precisely controls its final location and depth. This level of control is what makes it possible to build the billions of tiny, intricate structures inside a modern microchip. So in the end, by combining these incredible atomic-level cooking techniques, we take a simple, abundant element like silicon, and we methodically, precisely transform it into the powerful, intelligent brain that sits inside pretty much every piece of electronics you can think of. So we figured out how to add the ingredients to our silicon wafer, but that leaves us with a really big question, right? How do engineers actually draw the map for billions of transistors on that wafer to tell the ingredients exactly where they need to go? Well, that is a fantastic story for another explainer.